The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today we're going to talk about the integration of safety analysis into operational requirements. Having now understood the importance of power distributions, the importance of core heat removal, the importance of ultimate heat sink removal, we're going to try to translate those safety analysis results into what, in fact, guides the operator in terms of what he or she can or cannot do in operations and how we, in fact, operate these reactors. I'm also going to spend some time talking about the Reactor Oversight process and the Code of Federal Regulations, which controls everything that happens in an operating reactor. So there is a link, as you certainly now know, between the core design and how the plant is designed and the safety analysis. It's all bounded and guided by the NRC requirements, which are then translated into limits for operation. In order to be able to operate these plants, you have to create an organizational structure that is capable of implementing the operating requirements. There's a certain management team that is needed to make sure that the organization functions. And I'm not going to address it in this lecture, but there's a safety culture that is very important in terms of being able to assure that you can operate within a safety envelope. And this has become a very important issue today. So how do we get to the plant design, to licensing, to operations? As you now know, vendors such as Westinghouse, Combustion Engineering, formerly Combustion Engineering, now Westinghouse, Areva, they all propose plant reactor designs, and they're usually called the nuclear steam suppliers. What they do is design the core, and then another vendor like General Electric or Westinghouse couples the core with the steam turbines and the power supply systems. And then you have the architect engineer that in fact builds the plant or designs the plant given the structures, the fundamental structures that are available. So the vendor, say in this case, there would be a Westinghouse or a General Electric or Areva at this point, they would perform all the safety analysis and plant design that support the safety analysis, which demonstrates that the plant can be operated safely and you can produce the power that in fact is needed. So given the fact that the vendor is doing all this safety analysis report, they have to meet all these 10 CFR Part 50 requirements, and we'll go over that in a few minutes. The utility submits these reports to the NRC, and they submit their safety analysis and environmental report for review and acceptance. We now have a new process, and we'll touch a little bit on those. It's called the Part 52 process, instead of just the Part 50, in which you used to be able to submit a construction permit, get a license to construct, and then do the construction, and then a few years later, when the construction is almost done, you submit a final safety analysis report, and then you get an operating license, assuming everything is done. Right. Today we have the combined operating and construction permit at the same time. That obviously requires a lot more technical data and analysis to be reviewed, as opposed to a construction permit time when it's only called a preliminary safety analysis report. Then once the NRC is happy, then there's a possibility of licensing hearings. These are adjudicatory. It's like in a court of law before 3 judges. One's a legal person, usually the chairman, and you have one sort of nuclear engineer and one environmental engineer. And they sort of act as judges in an atomic safety and licensing board, where they in fact determine whether the interveners or the opponents of the plant have any legitimate reasons for not granting the license. And once that is all done, you are able to get an operating license. Now, the regulations that govern nuclear power are Part 10 of the Code of Federal Regulations. And I list the website there, and we're just going to go through that, just to make sure that you all appreciate that there is such a part, and it is, if all works well, there we go. you will be able to see what it contains. Title 10 of the Code of Federal Regulations. Now, this is sort of the Bible of the reactor designer and the reactor operator. It is used to determine how the plants are going to be designed. And if we start going through some of these things, I've highlighted a few parts. Part 2. Part 2 is a very important part because it describes, and all you do is click on it, it describes the conduct of licensing proceedings. So if you are ever curious about what is it that goes on when you need to file a license, you have possibility of a notice of public hearing. You have a very rigorous process for ultimately determining whether or not you are in compliance with the standards of the report and also the standards of intervention. There are petitions to intervene, requirements for standing. You just can't be a person living in Boston and you're going to be objecting to a nuclear plant in Colorado. You have to have some reason for objecting, which means you must be impacted by this. And then you file what are these called are contentions. And if you dig down even deeper, you can see it goes into what is it that you need to prove to be able to have standing and what kind of contention will be accepted by the licensing boards. And then these are adjudicated in a formal cross-examination procedure until such time that the licensing board has to make a ruling. That ruling is not quite final, but it can be appealed to the commission as a group. But the bottom line is there's lots of opportunity for public comment. And your future is really determined by this group called the Atomic Safety and Licensing Board. And again, it's an administrative judge, and there are 2 other judges who will be sitting and listening to the testimony. Much of it is technical, and they will in fact determine whether or not the contention is valid, and if it is, whether or not there needs to be any amendment to the operating license. Then we go back and we start looking further down the list. You have pre-hearing conferences. These are opportunities for, the interveners may file 150 contentions, only of which maybe 2 or 3 are admitted, because the admission standard is very strict because it must impact safety, and it must be something that hasn't already been decided by the judges. So these pre-hearing conferences are meant to reduce the list of things that need to be worried about during the hearing. Normally you go to hearing with about 4 or 5 contentions. You have general discovery. Again, it's just like a legal proceeding where the lawyers for the opponents and the utility and the NRC, you go and you decide, well, I need all this information, and you get that information as if you were being sued. It's really just about that. And these things take time, and then some of these hearings can take years to resolve. We haven't had one of these done in a long, long time, but my expectation is that once we start filing some more licenses, we'll be going through this kind of a process. And if you start looking through some of these other criteria and some of these other parts, the other part is Part 20. Part 20 deals with radiation protection. So if you're concerned about radiation protection standards, you can go into this Part 20 and try to see what the standards are. What are the occupational dose limits for adults, and also for internal exposure, for minors, for fetuses, and you keep going down for the public, obviously, and then there's also standards for the workers. This is an interesting part, which is once you finish the operating plant, you start decommissioning, there are already criteria published for license termination. So you go on, and These are all the things that you have to show that you can comply with during the course of the operation. The other part that's kind of interesting, which I flagged, is Part 21. Now, Part 21 is a general provision that says if you find anything that's generically applicable that could affect more than just your reactor, you are obligated to report it to the Nuclear Regulatory Commission. And then they go back and they decide how widespread is this problem, and they may issue other generic letters or statements to the other utilities that that this may affect your plant and you should check it. Now for example, let me give you an example. Suppose you're working for Westinghouse and you find an error in your calculation. The method is wrong, or you find something wrong in the calculation. And this methodology is applied to all the reactors that Westinghouse produces. That's a Part 21. And if you do not comply, there are some serious liabilities, and I'm not sure if they're criminal or not, but clearly the NRC does have rights to not only fine you, but also, depending upon the extent of the violation, get you into the legal system as a failure to comply to some federal law. It's equivalent to a federal law failure to comply. And you also have, it also spans to the director or responsible officer, director. So you can, in fact, reach much further than the poor engineer who made this mistake. This is a very important part of the federal regulations, because if there are generic defects, this part is the way to get at those. We also have fitness for duty programs, which is drug and alcohol. Any worker has got to be tested randomly for drugs and alcohol, and there are provisions for having to deal with that. The other part that I got to was Part 50. Now this part is the part that really guides the licensing of these and the design of these facilities. And it has this 50.9. This is a very interesting regulation as well. And that basically says if you know of anything that you said that was not correct, you have an obligation to come forward. And if you sign a letter that isn't completely truthful, and you withheld something that you possibly should have included, they can get you on failure to comply on completeness, not only accuracy. So this is a provision that the NRC had put in to be sure that nobody was not telling the whole story. It's a very important part of assurance of responsibility. In the nuclear world, you are allowed to, even though you may not have an operating license, you can get a license to allow for limited work authorization, which allows you to do certain construction work. Now, there are several types of licenses, as you see here. 104, which is therapy and research facilities, and 103 are for nuclear power plants and other industrial facilities. So most reactors obviously are under 103 licenses. And then you have this construction permit process. As you go further down, you have to provide certain information to the NRC, which this particular provision explicitly states in terms of what you need for a construction permit and licensing applications. You also have a standard form of technical specifications. And technical specifications are those things that describe your limits of operation, what you can or cannot do relative to power level, temperatures, and it has to fall into to support the criteria developed as a result of the safety analysis. Also, you're allowed to release radioactive materials from these plants, and you have technical specifications for those. You have to file emergency plans, and there are clear requirements for that. There's a fire protection rule, which addresses fires in the safety-related areas. And then you have environmental qualification of electrical equipment. Does anybody know what that means? If you have a loss of coolant accident, what do you get in containment? Steam, radioactivity, high temperatures. The equipment that you have to rely on in those events must be qualified for those conditions to operate. And there's a very strict rule to show that the equipment is in fact qualified for the service. The NRC may, after a period of review, define certain conditions of the licenses. A 5054F letter is show me, it's a letter saying, you need to show me that you should be allowed to operate because we have determined certain things. Prove to us that that you have met certain conditions. Then you have obviously criteria for issuance of the operating license. Then there are other very specific deterministic things that are applied. Acceptance criteria for fracture prevention measures in light water reactors. Very specific, basically dealing with reactor vessels. Fracture toughness requirements. Fracture toughness against pressurized thermal shock. Do you know what a pressurized thermal shock is? When you have an event, the reactor is operating at full power, you blow down the primary coolant, which is hot. You start injecting emergency core cooling water, which is cold. If the vessel is embrittled, namely radiation damaged, it can shock the vessel into failure. So pressure, and the reactor could be under pressure, especially for small break loci, and that could in fact fail the reactor vessel. This was a big issue for us at Yankee Row. We had to actually raise the coolant temperature of the emergency core cooling system because of the NRC thought our vessel was somewhat embrittled. And then you have anticipated transients without scram requirements. So you have all these general design criteria on top of which the NRC has decided to make specific detailed requirements to address some of these concerns that have come up. Loss of all alternating current power. Then you have another criteria, which is the accident source term. This is an arbitrary definition of what the source term will be in the event of an accident. It's not a mechanistic source term, it's an assumed source term, which obviously affects off-site release. They're now going to risk-informed categorization of system structures and components. These are kind of new requirements. So they're beginning to accept the notion of risk in regulation. And also, you'll see more of these as they're trying to risk inform the emergency core cooling Appendix K requirements. The NRC has a very extensive requirement for reporting licensee events. So if you have anything in particular, say you have a tech spec violation, that becomes a reportable event to the NRC. If you are operating outside the design basis, you must report it to the NRC. If you have an overexposure, you obviously have to report it to the NRC. And again, it's the plant tech specs and any operating condition which is prohibited, okay, by the technical specifications, you have to report. If you missed a surveillance that was required, an inspection, a test, you have to report those. So you have a lot of reporting requirements, and these LERs are rated by significance and category. What I'm trying to do is give you a sense of why these nuclear plants, in some cases, are a lot of trouble to operate. This is certainly much more extensive than a call or an outlet. One of the things, I remember one of my employees at Yankee worked very hard to get in this 5109 rule. It's backfitting. The NRC can, at any time they want to, make you change your design based on their perception of risk and value. We got a rule in place called the backfit rule that said you can't just do this arbitrarily. You have to show cost-benefit value for that change. And this rule protects against arbitrary changes in design or requirements, backfit. Obviously, if you violate your technical specifications, violate your requirements, you have violations. The NRC has a very strict process of if you, like you say, you violate technical specifications or your systems continue to have problems, they can cite you for violations, some of which are fined and some of which are unfined notices. And you'll see a section here on criminal penalties. Now, the two key appendices here are Appendix A, which are the general design criteria. So if you're starting off wanting to design a nuclear power plant, the first thing you have to do is look at what the general design criteria require. And these requirements are found in Appendix A. And I'm just going to scroll down here so maybe you can see. You got quality, you got design requirements for the reactor, the pressure boundary, the control systems, the fluid systems, testing requirements, containment design requirements. All of these are quite specifically identified as to what you must be able to do in the design of this reactor. So that's sort of your guidebook. The other major requirement is what we call Appendix B. Appendix B is the quality assurance criteria. If they can't cite you for a violation because there's no specific failure that fell outside the technical specifications, but if components fail, they can get you for failure to follow your quality assurance criteria, which should have prevented such failures. So this is their ultimate fine or notice of violation of last resort when they can't get you for a specific one. Then you start looking down the list of all these other appendices. Financial requirements, emergency planning, very specific requirements of 10 and 50 mile EPZs. We're not talking fracture toughness requirements, Appendix G, reactor vessel surveillance programs. I don't know if you know that every reactor has to put a surveillance capsule of the steel and the weld material they use in the reactor such that you can measure the neutronic effect as a function of time. And they have accelerated specimens. So they have specific requirements for how to do that. And then they have, what is this, numerical design objectives? Oh, this is ALARA. This is the as low as reasonable achievable radiation exposure. Containment leakage testing for these reactors. And then here's your famous Appendix K. We talked about that. These are the specific requirements if you ever want to get into it, what you have to do in they call these evaluation models in terms of what you must assume for the NRC to consider your analysis acceptable. And if you can show that you meet these criteria, when we talked about cladding damage and so on and so forth, the range of power distributions and peaking factors that might occur over lifetime should be studied. So these criteria are very, very explicit and specific that you must be able to show that your reactor can meet. As you can see here, swelling and rupture of cladding that you have to look at. And then you have the fire protection requirement. Earthquake, of course. This fire protection requirement, and you see they have dates that for reactors that operate before a certain date and reactors that operate after, because they recognize that you can't backfit certain reactors, but they sort of identify compensatory systems. Fire protection is still a very important area that has not yet been resolved. You'll see things like important to safety and safety related. Safety related is that is very clearly needed for safety. Important to safety says it's got to be available, but it's not as important as the safety related materials that have to be qualified. So I guess the purpose of this exercise is you'll probably never in your life have to do this, okay? Because if you're not in the reactor design business, you don't need necessarily to worry about it. But most students have not ever done it, and I thought it would be helpful for you to at least see it. Now, if you get to part 50, which is the one that affects the, I think I just did the 50, didn't I? Yeah, I jumped to the part 51, okay. So part 50 is really focused on the light water reactors and the 10 CFR parts 1 through whenever identify everything else you have to do. Now, we've sort of looked at this already, and now you can, I think, begin to appreciate why we, for the accident analysis, the LOCA is Appendix K driven, and we already talked about normal operation, infrequent activities, and also limiting faults such as the loss of coolant accident. And the safety analysis report, I think I showed you before, contains all of this information that describes the plant, including the quality assurance requirements, ends up with technical specifications based on the accident analysis. And then you have initial tests that you're going to use to confirm that the reactor is in fact operating as it's supposed to be. All of this is specified in that Code of Federal Regulations. Design basis accidents, we went over some of them. What we're going to do, I think, at the next lecture is look at some of these design basis accidents to see what are some of the important features that one needs to understand in some of these. And of course, the beyond design basis is the Class 9 leading to meltdown. We reviewed the notion that these were prescriptive and deterministic. Any computer code that you want to use for the safety analysis, you have to have NRC approval. And again, the results identify operating limits, what we call limiting conditions for operation. In other words, you cannot operate the plant unless all these systems are in operation. What your test and surveillance requirements are, which are driven by how you think and how reliable those plant systems are, and it's all summarized in the tech specs. So you've seen where in the origin of these things, which is part of this thing. Now, when you start building the plant or designing the plant, you have this Code of Federal Regulations. Then you have to also review, as part of your design, what these things are called generic letters. Generic letters are letters the NRC has issued to licensees about a problem. So in your design process, you have to make sure that you cover all of these generic letters on certain systems. NRC from time to time issues what they call bulletins and orders. If they find there's a problem, they can order every reactor to make a change. It may not be in the general design criteria, but it becomes part of your operating license or design basis because you now have to implement these things based on your reactors. NRC also issues information notices. If there is an accident in a particular plant or a failure of some kind, they will send out a notice to all reactors asking them to review this particular event to see if it applies to them. The safety analysis report plus all of this information becomes what we call the design basis, the plant design basis. And each plant needs to maintain its design basis document package, which has the current status of the plant and all of the assumptions that went into the accident analysis. If you get into trouble, the NRC can issue what is called a confirmatory action letter, which basically says, you must do this by such and such a time, or the order you be shut down. Or you could be ordered shut down, and you will not be allowed to restart until you comply with the confirmatory action letter requirements. And all the commitments you make in response to these things become part of your licensing basis. So, we have two things, a design basis, excuse me, and a licensing basis. Sorry. The licensing basis is all of this stuff that I just mentioned that summarizes your commitments that you make to the NRC. The design basis is really how the plant's designed, which may include some of this stuff, but this is what NRC basically watches out for, to make sure you're in compliance. NRC Oversight. We have typically 2 resident inspectors at every power station. If there is an issue, such as you might have a problem, and some of the recent problems have been leaks at some in-core instrumentation tubes, the Davis-Bessey event, for example, they will come in and and organize a special inspection team of technical experts and study that problem until they figure out what happened and why. You have these licensee event reports, which I talked about, that are self-reporting systems, that if you violate the technical spec, you must report it. And then you have, if you have violations that come out of these licensee event reports, or as a result of the resident inspector inspections, or the special inspections, they can cite you for numerous violations, which, depending upon the severity, can come to a fine. Now we have a new, relatively new, reactor oversight process, which is risk-informed, performance-based. And it is highly transparent. And what I'm going to show you is the transparency. And this is the part you want to pay attention to, because it has something to do with your homework. So let me just go to the reactor oversight process. They have certain cornerstones which they feel are very important. And they have reactor safety, they have radiation safety, and then they have safeguards, which is the security stuff. In reactor safety, they look at events that can create a problem, these initiating events in the PRA world. Mitigating systems, what kind of systems you have available to deal with these initiating events. Are the barriers intact, clad, primary system, secondary, containment? And how good are you relative to emergency preparedness, all of which are tested. In the safety, radiation safety, you have occupational and public radiation safety, and this is the security. So they have some performance indicators which they have chosen to use, and these are listed here: unplanned, for initiating events, unplanned scrams with normal loss of heat removal, and unplanned power changes. Unplanned power changes can result in transients, initiating events. Then you have emergency AC power, high pressure injection system. Now these are availability and unavailabilities. Is it available? This could be out of service. Heat removal system, residual heat removal, and safety system functional failures. That is, when you have systems that just don't perform, this is a bad one. Then you have, in terms of the barrier integrity, reactor coolant system activity, cladding failure, coolant system leakage, secondary failure. And then there's obviously one on containment. Emergency exercises, you have exercises once every 2 years, internal ones several times a year. Then you have your off-site notification systems that are tested. Then you have your drill participation. And of course you have occupational exposures. And this is RET's thing is called how much radiation you release off-site. Now, during the period, you have inspections done by the resident inspector. And if they have done an inspection, they'll give you a rating. Green is kind of good. And then you'll have a lot of these areas that for that particular quarter were not looked at. And you can, on the website, identify specifically what is done. So if you go to the NRC website, which is listed there, and will come up shortly, you will see this. Now, what we have here is actually right off the website live, and it gives you a list of options for operating reactors, and you can have a summary. Let's go see what the summary says for all the reactors in the United States. And you can see it's in the key areas. Initiating events, mitigating systems, barrier, emergency preparedness, occupational safety. If you have grains, now Brunswick had a white here. Now, where do you all live? Do you live near a reactor? What state do you live in?
California.
You live near San Onofre or Diablo Canyon. Close enough. California. New York State, where? Upstate. Fitzpatrick? In that area? Where's Fitzpatrick? That's kind of, where's Fitzpatrick? Where do you?
It's here. I live here.
Near Albany. Oswego, that's where it's near, Oswego.
Yeah.
That's Texas, sir.
Worcester.
Worcester. So you have Pilgrim and Seaver to worry about. So we can scroll down here and let's just take, white is the next level above green for a concern. Now, this is the mitigating systems that they have, which is another indicator of availability. Let's scroll down and see why they got a white. There's the white. It's a violation, okay? AC sources operating. Preliminary white finding with an apparent violation of tech spec, blah, 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 was identified for Unit 1. Finding involved inadequate corrective actions to prevent repeat failure of the number 9 main crankshaft bearing emergency diesel generator number 1. Failure to follow farm material exclusion control. Farm material exclusion control means this, when they were doing maintenance, they had stuff around and it fell into the machine and maybe cracked up the vessel, the generator. And failure to promptly identify and implement corrective actions to prevent emergency diesel generator from tripping on low lubricating oil pressure, which is apparently what the event was. When they did the inspection, they found that they had a failure involving a foreign material, and that should not happen, based on their quality control. So they may or may not get a fine. This finding is more than minor because it's associated with availability of emergency diesel generator number 1, which you need for loss of AC power. And it affects these cornerstones. This is sort of their justification. And this finding was low to moderate significance. And it was in a degraded condition for 3 days and in a non-functional condition for 5 days. Now, if you do your PRAs, you plug in the 3 and 5 days out of service. I remember I was just in China, and they had a failure of a diesel generator. It started to run, then it shut itself down. So I was talking to the STA. I said, can you just tell me what the risk significance of this event is on your plant? You put on the risk monitor, the risk doubled for 1 diesel generator out of 4 that was out of service. So you can see why NRC takes these kinds of things seriously, because availability of AC power is really important. Now, if you want to get the inspection report, now this is just a very small little summary, then you can get the sort of the full boat description on February 27th, what NRC thought of this. Okay? This issue is unresolved pending further NRC review. And it gives you all the background information that you'll ever want to know about what happened. They did say it was very low safety significant because it's into the corrective action program. They may or may not get a fine, but they have the ability to give you a fine. Now this SDP is a significance determination process. That is the use of risk to determine whether you are in the white zone or the green zone. Remember we talked about these little deltas, delta CDF curves? When you do the analysis, if that risk number changes by what that arbitrary change was, in terms of 10 to the minus 5, 10 to the minus 6, you will go into the white. They apparently got into the white based on that process. So that gives you all of the background information you'll ever want to have about this particular reactor. So the process is extremely transparent. Let's go see if we can find a yellow. Ah, Farley 2. What happened there? But you can see there's, even though they have green, they have what you call non-cited violations. Failure to maintain 2 ECCS trains operable due to gas accumulation in the charge and pump suction line. Self-identified. If you identify it by yourself, you get credit. And the fact that you are, CAP is corrective action program. Corrective action programs are an integral part of the safety of plants. Things will break, mistakes will be made, but if you have a good corrective action program, they will hopefully not be repeated. And that's what NRC looks like. So they're trying to give utilities some credit, even though you could argue it's a significant event here, possibly. But the fact that the utility found it and is taking care of it is given them credit for. Another one, a failure to promptly identify the complete population of service water valves affected by the system's corrosion environment. So again, this one is identified by the NRC, but they were able to, I guess, sort of justify that it's still in the green because the risk significance wasn't that great. And what happened to the yellow? But there's an awful lot of excellent information, and every one of these has an inspection report associated with it, either by the NRC resident or by the special inspection teams. I think I have, unfortunately, looped myself here. Stuck. Back up here. Continue. I won't send it. I just lost it. Okay, I think we've had enough of that. But the point of this is that we have a lot of good information out there that you can use to follow this. Now, in terms of operation, we've obviously got some rules. I've just talked all about the rules. You've got to have some skills, which means operators are trained and so on and so forth. But you also have to understand things. If you look at 3 Mile Island, they had plenty of rules, which they were all in compliance with. They had certainly skills in terms of how to operate the plant, but they didn't have adequate knowledge about the implications of what was going on. And so this triangle was a little bit distorted. From the NRC's perspective, their role is to make sure you're in compliance with all regulations. At present, they do not regulate safety culture, but they're attempting to move into that area. You need to operate within the safety envelope that's defined by the technical specifications. The most important of which are maintaining your critical safety functions, which is reactivity control, core heat removal, secondary heat removal, and containment integrity. This is the cornerstone. And when they prepare these risk monitors, they also have safety parameter display systems. They're completely based on identifying quickly whether you've lost any of these functions. And of course, the utility would like to make electricity in the process, which is sometimes difficult. So, managing the safety of the plant is the safety envelope defined by the technical specifications. And the entire plant operation is procedure-based. There's no, cowboys. And they're operating procedures. If the plant is not operating in a normal mode, they have developed abnormal operating procedures, which is if certain pipes break, what would you do if that occurs? Or if certain pump doesn't work, what would you do if that occurs? And many of these operating and abnormal operating procedures, and certainly abnormal emergency procedures, are symptom-based. They used to have procedures that said, if pump number 1 breaks, you do this particular step. If pump number 2 breaks, you do this particular steps. However, they found that pumps don't always break in that order, or things don't always happen in the way people have postulated. So they have symptom-oriented operating procedures, which most of the new plants and old plants have converted to, where if you lose function, this is how you restore function. And these are the things you try to restore that function, both in the abnormal and emergency. Emergency is when obviously you have issues where you are losing coolant, possibly loss of coolant, possibly loss of function. You have maintenance procedures. Every piece of equipment has a procedure associated with how to maintain it. There are obviously a lot of procedures in engineering design, independent reviews. So if you're in the engineering design office, you've got to follow a rigorous step of design procedures to make sure that you are in compliance with quality assurance on the engineering side. Of course, there's security, and then there's radiation protection. So the bottom line of this message is managing safety is based on technical specifications and very strict procedures which you must follow. And the reason that they do procedures is because it provides a standard. You don't want new crews operating with new ideas. You want them to operate in a fixed, predictable way. Here's a slide of what we call the safety envelope, and it's from the IAEA. And I guess the best way to look at this is to sort of look at from the top down. This is the safety limit. If you exceed this thing, something will break. Either fuel or a vessel. Then you have safety system settings, which are set in a way that if you are in a transient, you will, and if that safety system set point is engaged, in other words, you exceed it, the plant shut down, you will hopefully be below the limit, the safety, ultimate safety limit. Then you have below that operating limits, which are where you don't want to strain the reactor, but this is sort of what we would call your administrative limit. You don't want to be kind of in this zone. Your alarm set points are much lower, and your normal operation could be down in here. So you have certain margins of operating, which would be in this band, and your alarm set points kind of trigger you to keep within your operational limit, and you can restore to steady state operation. And then above that is where your ultimate safety protection systems will keep you from getting into bad trouble. This does have recognition that everything will not happen automatically. Okay? So operators can, in fact, delay. But the bottom line is most of this stuff is automatic, and the operator doesn't have any chance and should not be intervening with the set points. So margins are built into all these kinds of settings. We've seen this picture, or seen this to a control room, where you have a lot of the instrumentation, a lot of switches, as you'll see at the simulators, and a lot of instrumentation that you can display. Right now, more and more of it is going onto computers, and less of it is being used as physical hardware where you have switches on consoles. But the tools, obviously, for control are the automatic trips. We went over some of those when we looked at the loss of coolant accident. The safety parameter display system, I think I'll see if I can find one for you of a representative of a new plant. You have risk monitors, which I think we'll look at again. And then you have what we call these key process and control parameters, which allow you to operate within a certain band. This is your risk monitor. We saw this before, where you have your daily operation. You have your sort of internal warning limits and areas where you do not want to exceed. This is, I think, 10 to the minus 4. Core damage frequency, large early release frequency, and trip likelihood. So these are now routinely used in control rooms. Now, how do you organize a plant to make sure you can administer all these things? Typically, each one of these plants have, and if it's more than one reactor per site, has a site VP and a plant manager. You have an operations group with their shift technical advisors, safety technical advisors. These are the independent eyes and ears of the operations department, maintenance, engineering. Of course, some reactors have large engineering plants, large engineering staffs at sites. Some have centralized engineering at various locations. Radiation protection group, security, and a quality assurance group. So depending upon how the company wants to organize itself, there's very clear responsibilities. Engineering, as I said, may be centralized. A typical non-outage day. First thing in the morning, 7 o'clock, whatever, you get into the plant. What happened yesterday, overnight? What's the operability status of the reactor? And some people actually track days since the last human error, which is an interesting unit. Then we have limiting conditions for operation. The control room operators provide a briefing, they have a turnover, and then they kind of review what has happened overnight and what's going to happen today. Then the risk monitor, they kind of look at the plant status based on what's operable and what's not operable, and they make adjustments. And then they establish a plan for the next shift, what maintenance and tests are being done. They'll update the risk monitor to acknowledge that this stuff will not be available, and that risk monitor will tell them there are certain things that to be aware of. And they go obviously into the electric generation. Now the oversight process of the plant is a little bit different than that of the NRC. So, as I mentioned earlier, they have a corrective action program, which says anytime you find a discrepancy, any deficiency, anything out of the ordinary, all employees are encouraged to write this up into the corrective action program. And you write what is called a condition report. And there could be thousands of condition reports every year. Each condition report is evaluated for its significance, responsibility assigned, priority assigned, and addressed. Then they have a corrective action review board, which is a group that maybe meets once a week, maybe a couple of times a month. And they review all of the corrective actions that have been taken, and to try to identify whether there are any trends. Are there things that we're seeing, especially in human error, that are repeating? Are we seeing aging effects? What is it that we can learn from all these reports? The objective is not to reduce condition reports to zero, because as I said, that's extremely difficult, but to be able to manage the deficiencies, manage the risks. So this is, if you have a strong corrective action program, you are likely running a safe plant, even though you may have a lot of events. And some people look to the number of events that are reported as an indicator of a healthy corrective action program, particularly if you can address them. The quality assurance department isn't necessarily involved with the corrective action program, but they oversee tests, surveillances, design changes, things that they have a regular audit program, and they do what you might call peer inspections. In other words, when people are doing some maintenance work at the plant, they're overseeing that to be sure the procedures are being followed. You have a plant operations review committee, there should be a bullet here, which is a committee that is organized by the plant that reviews all design changes, all changes in procedures to make sure that they are appropriate for this plant. So if an engineer proposes a certain design change, it cannot be included in the plan design until this committee and a whole bunch of other people review and approve it. You also have a Nuclear Safety Advisory Review Committee. These are not just the plant people, and this includes these plant operation review committees, could be health physics people, maintenance people, operations people, engineering people, as a joint group from the plant. This group could be more of a corporate-wide organization. They review and approve, then this group independently reviews and approves before any design change is made. That's what they call it. Some companies, most now, have external review boards. People like me serving on an independent group, looking at, 3 to 4 times a year, how the plant is operating, looking at how the strength of the corrective action program, looking at failures. So these are independent people that provide independent oversight to management to allow them to get an independent check of what's going on at their plants. And I'm sure you are aware now of the Institute of Nuclear Power Operations that was organized as an industry self-regulating group organized after the 3 Mile Island accident and has been very effective in improving and upgrading all plants to certain high standards of performance. That's not to say they have not missed things, like the most recent Davis Bessie event. But they get into areas of engineering, operations, maintenance, and they have training programs accredited, just like a university program would be accredited for training of operators, engineers, maintenance engineers, and so forth. So a lot of help, if you will, in terms of assuring the safety of these plants. Message there is, once the plant is built, it's not over. It's a continuous process of improvement. We put this chart together. It says key success and performance factors. And this was put together, we ran a workshop in Slovenia, and we had lots of internationally well-experienced people. And we asked them to rank what they thought were the most important safety factors to determine whether a plant is going to be run safely. And look what came to the top of the list. Now, why did it come to the top of the list? The argument is that if you could have 2 equally well-designed plants, let's take Millstone Unit Number 1 and Vermont Yankee, or Pilgrim. Same design, same vintage. One operated extremely well, and the other got shut down. And the safety culture of the management and the attitude of the workers made the difference. How they chose to operate. The other important element, which is the next important element, is the basic design of the plant. Is it fault tolerant? One could argue that the Babcock and Wilcox plants were not fault tolerant. They relied on everything working perfectly. One could argue that the pebble bed reactor is hugely fault tolerant because even if it's not operated very well, it's very hard to melt, if not impossible. So basic design of the plant and being fault tolerant is really important. Then comes training in all basic areas as the third most important feature, because this gets into the skills level, the knowledge. And then quality assurance. What kind of oversight do you have of this operation? And are you focused on self-assessment or some cop watching what you're doing? And you could argue the cop could be some internal QA guy or the NRC. How do you organize your plan to sustain this safety? Extremely important. You can have a dysfunctional organization with a perfectly safe plant and it'll be completely not as good as you want it to be, or safe. Notice the last item for success in safety was the regulations, judged by this group, which I cannot disagree with. And what everybody concluded was that the regulations need to motivate safety. 3 Mile Island was in compliance with the regulations. The problem was the regulations did not motivate safety. They gave you a false sense of security, that if you meet the regulations, you are good. Wrong. Because you had inadequate knowledge perhaps inadequate safety culture. The basic design of the plant was weak. Training was obviously not as good as it needed to be. And self-assessment wasn't even a concept considered in those days. So this is sort of the bottom line message. Now, for the homework assignment, I'm glad you're paying attention relative to my zipping along with the internet sites. Use the Reactor Oversight process site, and identify the key safety issues in the last 2 quarters of the reactor nearest your home. I want you to feel comfortable about your own neighborhood nuclear plant. And based on the review of performance indicators, identify the particular inspection reports upon which this, it'll be on the web, I posted it already. Identify that, why these findings are done, what the findings are based on, and give me a 2-page memo about the condition of this plant overall. So you're looking at the whole big picture, all of the cornerstones, to see whether or not you think the appropriate corrective actions have been taken. That's why I want you to go back a couple of quarters. And are you satisfied with the safety of the plant? So you're the regulator, okay? The fun part is to be able to go and dig through this stuff. And I call. So, any questions on the assignment? It'll give you a sense of what's really out there, and I think an appreciation of how exhaustive the process can be. And that's why the staffs of these reactors are so large. Now, the last thing before we wrap up, I want to put this chart back on there again, because this chart is a schematic of a complete plant, and I don't know if I can have a better picture of it, but if I can find one for next class, I will. But what we want to be able to do is kind of think through how this reactor, steam generator, and pressurizer are interconnected with all the systems. So, for example, if I could read this, and I could find out where the feed water pumps were. If those fail, I'd like you to, we're going to talk about what happens and why. And we'll look at some of the transients and accidents that are in the safety analysis report, and we're going to talk about what happens to the core next class. So we'll start to think like an operator, like an engineer who says, what is my most important function here in this reactor? And that's easy. We have to keep water there. Because if we don't have water here, you're going to break barriers. That's the most important thing. When I was at Yankee, we were going to design this very advanced reactor, and we called it, instead of an emergency core cooling system, we wanted to call it keep the core covered cooling system. And that's the deal. Keep the core covered. You can make a mess, but you're not going to have a major release of radioactivity. And so once we start thinking about breaks in the main coolant pumps, pressurizer relief valves not opening, sources of water, makeup water, we'll kind of work through this because I think it will give you an appreciation of the dependencies of what we might call the non-safety systems like these turbines to the ultimate heat sink, ultimate heat removal of this reactor. And once you get that feeling, I think you will have gotten what is needed to be gotten out of this course. Because the operators obviously can determine how much water gets in there. And the plants that have the lowest core damage frequency are the plants that have the most number of means of getting water to the core, even if they're not safety related. That's why in the PRAs, you'll see very, very low numbers for core damage frequencies for plants that can take credit for a water system that may be buried over here and provide water into the core. In BWRs, one of the things that saved some of these plants in the early days was the water that went into the cooling of the control rod drives, as I recall. That was just enough water to keep that core, and that may have been the Browns Ferry event, as I remember. I'll check it again. But it's really important to understand the dependencies. When I gave my class affairs lecture, we talked about the heat in plus the equal to heat out. Okay, very simple concept. And we went through the precursor event of 3 Mile Island was Davis Bessie again, always was coming up. And the students were getting it. They were saying, well, if you lose cooling here, this thing expands, the water in the reactor expands, expanding the water in the pressurizer, which shows you've got plenty of water in the core. When in fact, you were losing it. Confusing signal, right? And then when you started inserting water in the core, what happened? You cooled the vessel water, it shrunk, and your water level was going down in the pressurizer. And they're saying, whoa, why is the water going down when I'm adding water? Where's the water going? Okay? They didn't get it, is what I'm trying to tell you. And the important thing is to get it, understand where the water goes and understand how you can remove heat. And that's really the key here. And we'll work on this, maybe a clearer version of this chart next time. Do you have any questions about the regulatory structure for NRC's role?
I'm particularly interested in the sort of generation 3.5 reactors that are being proposed. They have ESBWR, EPR, AP1000, etc. Will we be looking at those and sort of what hurdles they face? Or also, I know there's sort of a new regulatory process, right?
R52.
Yeah. I mean, I've been told kind of briefly what the changes are,
Okay.
but I haven't seen exactly kind of what they are.
Okay, I'll actually do that. I'll put that on the list of topics, Part 52, and how the new reactor designs have changed the safety philosophy. Okay, just very briefly, since we have a minute or two. EPR is a bigger version of this with more redundancy. It's more robust. And they've added a core catcher in the bottom of the containment. So in the event of a fuel melt through the vessel, they'll be able to say that we can not have a recriticality. And we can manage the pressure spike. So it's a much more robust basic reactor. I don't know if you heard David Lockbaum when he was here. He likes the EPR because it's more robust, more rugged. The AP1000s, they have decided to innovate a little bit more. And they started to use more of the passive systems. So EPR is engineered operating operable systems, pumps, motors, backup electrical generators, and if everything else fails, alcohol. Westinghouse went to more passive systems. We're not going to rely on pumps to pump water. We use gravity to do this. And the gravity, some of you, may not be as reliable as active systems, which is a big debate here at MIT right now. So there's a big discussion about, they'll have a big old water tank in the ceiling of this containment, which literally flushes into the reactor, and it's positioned in such a way that when all that water flushes into the reactor, it covers the core. No sump recirculation needed. So I think that's a good exercise, kids. We'll take a look at some of the innovative designs and see how people have thought about it. On the ESBWR, they have decided to make a natural circulation reactor where you made a very, very tall reactor with a chimney. And we haven't talked about BWRs yet, but prior to doing that, I'll give you a brief introduction to how a boiling water reactor works with recirculation pumps, internal recirculation pumps. They got rid of those, and they're using natural circulation to cool the core. Again, more passive, but they still have feed water pumps. So, but that would be a good exercise with the Part 52 process. We'll see if we can work that in. I know I have 1 or 2 lectures that I've already covered design and licensing basis. I think I've given you all I need to do on that.
For sure.
Okay, any other questions relative to process, regulatory roles? The regulator is real, and they are there. And at the plant sites, I know at Yankee when we had our resident inspectors, they were everywhere, 24 hours a day. They could look at anything. So, okay, good. Thank you.